Good morning to everyone. I'm Dr. S. Malathi, Associate Professor, Department of Chemistry PG, Velalur College for Women, Erode. In this module, I'm going to discuss about phase rule. Generally, phase rule expresses the relations between phases, phase compositions, and variables like temperature and pressure in a system of a given composition at equilibrium. Phase rule is deduced by Willard Gibbs in 1876. Generally, phase rule is related with what is meant by phase, component, and degree of freedom. These three things are interrelated to phase rule equilibria. So, phase rule is mathematically expressed by F is equal to C minus P plus 2. Here, F is the degree of freedom, C components of the system, and P is the phase. The component are defined by chemically independent constant of a system, any system, that is solid and liquid both are considered as a single component, and whereas in gas is an ignorable one. So the degree of freedom is related to component and phase of the system. So the minimum number of independently variable factors such as temperature, pressure and concentration, which must be specified in some system completely. That is, F is equal to 0 means non-variant, and F equal to 1 means the system follows univariant. F is equal to 2 means bivariant, and 3 means trivariant. So generally, phase diagram is sub-categorized into two categories, that is PT phase diagram and TZ phase diagram. PT phase diagram, the graph is drawn between pressure and temperature, whereas in TZ phase diagram, the phase diagram is drawn between temperature and composition or concentration of the any system. Now we are going to see about phase rule, that is one component water system. Here the water exists in three forms, that is solid, liquid and gas. Here phase is 3 and component is 1. Because the component is chemically same, that is same molecular formula, that is H2O, but phase is solid, liquid and gas. So the phase value is 3. So we put component and phase in degree of freedom formulae, that is phase rule, F is equal to C minus P plus 2. The value becomes 0. So the system follows non-variant. This is the phase diagram of one component water system. Here some salient features in diagrams, that is curves, OA curve, OB curve and OC curve, and area of one component system, that is AOB, BOC and COA. Here curve OA exists between liquid and gas, that is called vaporization curve, because liquid is converted into gas phase, so it is called vaporization curve. Here the degree of freedom value becomes 1. In same way, the curve OB is called melting point curve. Here the water liquid and solid ice exist between these two phases, that is called melting point curve. Here solid is converted to liquid, so the degree of value becomes 1. And same thing, curves OC is called sublimation curve. Here the solid ice is converted to vapor gas. Here also the degree of freedom value becomes 1. So commonly the curve OA, OB, OC, the system follows univariant. Next we move to areas or triple point. Here the triple point system, the curve OA, OB and OC meet at a point O. That point is called triple point. Here the phase is, generally the phase is 3, component is 1, so the degree of freedom value becomes 0. So this system is non-variant. Next we are going to areas of one component system, BOC and COA and AOB. Here the system follows bivariant, because the area COE contains or occupied only one phase. In the same way COA and AOB. So the degree of freedom value becomes true. And final one is metastable equilibrium. Here the curve OA extended up to OB dash Here the water is converted into supercooled water and vapor system. Thank you all.